This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal. Today I am going to discuss the ARM processor instruction set, under which the category we are going to discuss is data processing instructions. These slides are prepared by referring the textbook ARM, a System Developer's Guide Designing and Optimizing System Software. Authors are Andrew Enslows and Chris Wright. Publication Morgan Kaufman Publishers. The data processing instructions manipulate data within registers. They are move instructions, arithmetic instructions, logical instructions, comparison instructions, and multiply instructions. Most data processing instructions can process one of their operand using the barrel shifter. If the S is added as suffix for a data processing instruction, then it updates the flags in the CPSR register. These instructions only work on registers but not on memory. The various data processing instructions consist of, under data movement instructions, we have move, MOV and MVN instructions. Under arithmetic instruction, add, ADD, ADC, SUB, SBC, RSB, RSC. Under logical instructions, we have AND, OR, XOR, bit clear, BAC. Under comparison instructions, we have the instructions are CMP, CMN, TST, TEQ. Under multiplication, we have MUL, MLA, both short as well as for long. That means for 32-bit data as well as for result of size 64-bit. The syntax of data processing instructions are operation, condition is optional. I'll put a star for this. S is also optional. If S is specified, it will update the flags in the CPSR register, RD, RN, and operand 2. The second operand is sent to AL through barrel shifter. The data movement does not specify the RN instruction, whereas for the remaining instructions, RN also will mention. For arithmetic logic unit in ARM processor, one input is given directly as non-pre-processing data, that is through RN register. The second data will be processed either with or without pre-processing, that is RM. That will be given for barrel shifter for shifting left side or right side or rotating left side or right side. Then this barrel shifter output, which is N, that will be passed as second input for ALU, and the result which is produced here it is RT. The data processing instructions are processed within the ALU. One operand passed through RN register and the second operand with or without barrel shifter. A unique and powerful feature of ARM processor is the ability to shift the 32-bit pattern in one of the source register left or right by a specific number of positions before it enters into ALU, which will be passed through barrel shifter. So for the instruction which we are executing for arithmetic instruction ALU, one operand will be passed through RN, the second operand will be passed through N, and the result is RN for most of the instruction except move instruction. Under barrel shifter, the various shift operation which we can give through value of N is as follows. If it is the immediate data, we are going to be provide the data with hash. Suppose if I want to send the data is 46, then we will write hash 46. Hash indicates it is an immediate data. The operand, second operand, we can pass through a register, that is through RM, without any shift operation. Logical shift by an immediate, that means RM, comma, LSL hash shift immediate. Suppose if I have the instruction, the second operand is right like this, RM, LSL hash 4. This indicates the RM contents will be shifted left side by 4 bits. Similarly, logical left shift by register, RM, LSL, RS. This RS contents will be left shifted. Logical shift right with immediate, RM, LSR, hash, immediate data. Logical shift right with register, RM, LSR, RS. Arithmetic shift right with immediate, that is RM, ASR, arithmetic shift right, shift number, that is shift immediate data. Arithmetic shift right by register, RM, ASR, RS. Rotate right by immediate, RM, ROR, rotate right with immediate data. So that will be provided with hash. Rotate right by register, RM, ROR, RS. Rotate right with extend, RM, RRX. There are few data processing instructions that not use the barrel shifter. For example, mul instruction for multiplication, CLZ count leading zeros, and QADD signed saturated 32-bit add instructions. Data movement. These instructions copy the data N into the register, that is target register, which is RD. The various instruction under data movement are MOV and MV1. The syntax of the instruction is operation, conditional, which is optional, S is an optional, RD, comma, N. Under move, we have two types of move instruction. One is MOV, another one is MV1. MOV instruction. This instruction move a 32-bit value into the register which was specified in the instruction. Syntax of the instruction is MOV, RD, comma, N. This instruction move the value N into the register RN, into the register RD. So that is N value will be moved into RD register. The next one is MVN, move negate, which will move the not of the 32-bit value which was specified in N into the register. The register which we are having the target is RD. The syntax of the instruction is MVN, RD, comma, N. This 32-bit value which you are placed in N, that will be complemented bit by bit and it will be moved into RD register. So this instruction move the complemented value of N into the register RD. RD is occupied with the negation of N. Here we have few instructions under move. We will see MOV R7, comma, R5. So this instruction will copy R5 contents into R7. So the R5 contents will be placed in R7. MOV R7, comma, R5, LSL hash 2. So this is LSL is shift towards left side. So this R5 contents, after shifting towards left side by 2 bits, the result will be placed in R7. So the first operation here it will do is shift R5 contents by 2 bits and this shifted data will be copied into R7. Move R0, comma, R1, LSL hash 1. So here the contents of R1 will be shifted by 1 bit towards left side and this will be copied into R0. When we are moving this, if you are added S as suffix, then the flags will be updated. The next category is arithmetic instruction. This arithmetic instruction implement addition, subtraction of 32-bit signed and unsigned values. The various instruction under arithmetic category are ADD, ADC, RSB, RSC, SUB and SBC. The syntax, the general syntax of the arithmetic instructions or data processing instructions are instruction followed by conditional, which is optional condition, then sign for updation of flags in CPSR, so this is also optional, RD, RN and N. So here the source data is provided in these two registers, RN and N. So whatever the instruction which was specified on these two data it will perform and the result will be moved into the RD register. First we will see the first instruction, ADD. This instruction add two 32-bit values. The syntax of the instruction is ADD, RD, RN, comma, N. Here I am not using any S as well as any condition we are not provided. I will show with respect to example how you have to use the condition as well as S. This instruction add the contents of or the value which it is stored in RN register with N. The resultant sum of Rn plus N will be moved into RD register. So the functionality of this instruction we can write as expression RD is assigned with Rn plus N. For add instruction, if S suffix is added, then ADDS, RA, RD, RN and N. This instruction also will add the contents of Rn register with the N value, and this result after adding these two values, the result will be placed into RD register. The difference between add instruction and ADDS instruction is the CPR updation will be takes place when we are given a suffix S for add instruction. The next instruction is ADC, add along with carry. This instruction add two 32-bit data values along with the carry flag. The syntax of the instruction is ADC, RD, RN and N. So here Rn contents will be added with N along with the carry flag and the result will be placed in RD register. This instruction add a value stored in the register Rn with N along with the carry flag. The result is stored in RD register. So the expression we can write as RD is assigned with Rn plus N and carry flag. If S suffix is added, the same functionality same as that of ADC. When we are added S, it is going to update the CPR register with the flags. Depending upon the result, the flags which are there in the CPSR that will be updated. The next instruction is RSB, which is a reverse subtract of two 32-bit values. The syntax of the instruction is RSB, RD, RN, N. This instruction subtracts Rn from N and the result will be stored in RD register. This instruction can use to negate numbers. The functionality we can describe as RD is assigned with N minus Rn. Whereas if you add a suffix S, then it is a reverse subtraction with updation of CPSR. So that we will write as RSBS, RD, Rn, N. This instruction will subtract the contents of Rn from the register N and the result will be stored in RD register and it will update the CPSR register based upon the results. The next instruction is RSE, reverse subtract with carry of two 32-bit values. the syntax of the instruction is RSB, RD, RN, N. The source contents or the source values we are going to be placed in Rn, and the barrel shifter output, that is N. The value is subtracted from Rn value is subtracted from N along with the carry flag, and it will be stored in RD register. So the RSB instruction subtracts Rn from N along with the carry flag, return to the result into RD register. This instruction can use to negate numbers. The syntax, the functionality we can describe by equation is equivalent to RD is assigned with N minus Rn and the complement of the carry flag. When you add a suffix S for RSB instruction, it will update the CPSR depending upon the results which are affected to the flags. If S is not given, the CPSR will not be updated. The next instruction is SUB. Subtract two 32-bit values. The syntax of the instruction is SUB, RD, Rn, N. Here, this instruction subtracts N from Rn and writing the result into RD. The functionality we can describe it as RD is assigned with Rn is subtracted with N. If S is added for SUB instruction, whatever the result is obtained, it will update the CPSR with the respect to flags. If S is not given, the flags will not be reflected in the CPSR. The next instruction is SBC. Subtract with carry of two 32-bit value. The syntax of the instruction is SBC, RD, Rn, N. This instruction subtract N from Rn along with the carry flag, and the result or difference will be returned to RD register. The functionality we can write as RD is assigned with Rn minus N minus carry flag. If S is added for the SBC instruction, it will update the CPSR registers with the reflected flags. At a glance, you can see all the arithmetic instructions. The various arithmetic instructions we are having is add. This is for add two 32-bit values. The functionality we can write as RD is equivalent to Rn plus N. ADC, add two 32-bit values along with the carry, that is RD is equivalent to Rn plus N plus carry. RSB, reverse subtraction of two 32-bit values, that is RD is equivalent to N minus Rn. RSB, reverse subtraction with carry of two 32-bit values. The output is written to RD, which is equivalent to N minus Rn minus carry flag complemented. SUB, subtract two 32-bit values, that is RD is equivalent to Rn minus N. SBC, that is subtract with carry of two 32-bit values. So RD is equivalent to Rn minus N minus complemented carry flag. Few example under arithmetic instructions we will see. SUB R0, R1, R2. So here R1 is subtracted with R2 and the result will be placed in R0. Here in the example, R1 is given as 0, 0, 0, 0, 0, 0, 0, 2. This will be subtracted with 0, 0, 0, 0, 0, 0, 0, 1, which gives the result as 2 minus 1 is 1. The rest of the bits are zeros, so we'll get the result as 0. This will be moved to R0. Suppose if you have SUBS R1, R1 hash 1. So here the data which is immediate, so it will do R1 register minus 1. R1 register content is 0, 0, 0, 0, 0, 0, 0, 1. Subtract with 1 So we are going to get the output as zeros. As the result is 0, the jet flag will be 1. So it will update the jet flag as it is given a suffix as S. So now before execution of this instruction, the jet val is lowercase, indicate it is reset. Because the result is 0, the jet flag will be 1, that we are representing as capital Z in CPSR. If S is not there, the CPR updation will not be takes place. RSB R0, R1, hash 0. So RSB instruction will do n minus R1. N minus R1, where n is equivalent to 0 and R1 is equivalent to 00000077, which is in the hexadecimal representation. So which will get as 000000 minus 00000077. We need a carry, that is 16. 16 minus 7. 16 minus 7 will get 9. Here left out is 15. 15 minus 7, 8. Here we are going to have 16 minus 1, that is 15. 15 minus 0, 15 in the decimal. In the hexadecimal, it is equivalent to F, 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 and F. So the result which will be stored in R0 is equivalent to FF, 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 89H. As S is not suffixed, there is no updation in CPSR. If it is given with S and it is a non-zero value, so jet flag will not be set. Now we will see the instructions, the variation with respect to barrel shift operation. So for ALU, one data directly we are sending to the instruction in Rn plus. The second one we are placing n through some operations performed by barrel shifter. The input for this one is some register Rm. The result we are taking as RD register. The wide range of second operand operation as shift available on arithmetic and logical instructions is a very powerful feature of the ARM instruction set. Assume the instruction we are having is ADD R0, R1, R1, LSL hash 1. So this instruction will do the addition of R1 with the left shifted by 1 bit of the R1 content. Assume before execution R1 instruction is equivalent to R1 register content is equivalent to 00000005. This we have to shift towards left side by 1 bit. So 5 means we will get 1, 0, 1 and the remaining bits are zeros. When you shift these contents towards left side, we are going to get the value as 1, 0, 1, 0 and the upper bits are zeros. This is R1 LSL hash 1. Left shift the contents of R1 by 1 bit. So now the equivalent value we are going to get, here it is, earlier it is 5. Now after left shifting we are going to get 8 plus 2, 10 in the decimal. In the hexadecimal it is 8. So here after left shifting R1 LSL hash 1 will give us as 00000008. Now we have to add these contents. By the addition of these two, A plus 5, A is decimal equivalent is 10, 10 plus 5, 15 in the decimal, its hexadecimal is F, 0 plus 0, 0, 0, 0, 0, 0, 0, 0. This will be moved to the destination which is R0 register. So after execution, R0 content is equivalent to F, whereas R1 contents will not be updated. Only the shifted value will be added to the R1 register, but this shifting will not be updated into R1 register. So register R1 is first shifted by one location to the left to give the value of twice of R1. When you shift the contents towards left side, the value of that particular register will become double. The add instruction then add the result to the barrel shifter operation to the register R1. So as it is double value, that I can take as 2R1. This we are going to add to the R1 content. So in total we can say the 3 times of the value of R1 will be moved to the destination register R0. The next category is logical instruction. Logical instruction perform bitwise logical operations on 2 source register. The various instruction under logical instruction category are AND, ORR, EOR and BIC. The syntax of the instruction is any one of these instruction followed by conditional, which is optional, S, which is optional for updating CPSR, RD, RN and N. The source values are placed in RN and N. RN is no pre-processing data. N is pre-processed with or without pre-processing. The destination is RD. The logical instruction update the CPSR flags only if S suffix is present to the instruction. These instructions can use barrel shifter for providing the second operands in the same way as that of the arithmetic instruction. The first instruction under logical instructions are AND, that is logical AND, AND, logical bitwise AND of 2 32-bit values. The syntax of the instruction is AND, RD, RN, N. This instruction will perform bit by bit AND operation between RN register and N value. The result will be stored in RD register. The functionality we can write as RD is assigned with RN, logical AND with N. If S is added as suffix to AND instruction, it will update the CPSR register with the respective flags based upon the result obtained, which we are moving into RD register. The next instruction is ORR. It is logical bitwise R of 2 32-bit values. The syntax of the instruction is ORR, RD, RN, N. This instruction will perform bit by bit OR operation between the value which is stored in RN register with the value of N, and the result will be stored in RD register. The functionality we can describe as RD is assigned with the logical OR operation between RN register and the value of N. If S is added as suffix for ORR instruction, apart from doing the OR operation between RN and N, the result will be moved into RD. Apart from that, it will update based upon the result the flags in the CPSR register. The next instruction under logical instruction is EOR, which is logical bitwise XOR of 2 32-bit values. The syntax of the instruction is EOR, RD, RN, N. This instruction perform the exclusive OR bit by bit between the value stored in the register RN with the value N. The result is stored again in RD register. The functionality we can write as RD is assigned with RN, exclusive OR with N. Here, cap indicate it is a representation of exclusive OR operation. If S is added to EOR instruction, it will also perform the exclusive OR between RN and N. Based upon the result, it will update the CPSR register also, apart from moving the result into RD register. The next instruction under logical instruction is BIC, which is logical clear, which we can have the functionality as and not operation. This instruction is particularly useful when clearing the status bits and is frequently used to change the interrupt mask in the CPSR register. The syntax of the instruction is BIC RD, RN, N. This instruction logic bit clear bit by bit between the value stored in Rn register with negation of n, that is complement of n. The result again it will be stored in Rd register. The functionality we can write as Rd is assigned with Rn logical and with the complemented n value. If S is added to BIC instruction, based upon the result, it will update the flags in the CPSR register. Now we will see few examples related to logical instruction. ORR R0, R1, R2. So here R1 register contents will be ORed with R2 register contents. Here the R1 contents we are having is 0, 2, 0, 4, 0, 6, 0, 8. This will be ORed with 1, 0, 3, 0, 5, 0, 7, 0. 8, I am taking only the LSB digit, that is 8 we can write as 1, 0, 0. 0 we can write as 0, 0, 0. Now we will get 0 and odd with 0 will get as 0. 0 odd with 0, 0. 0 odd with 0, 0. 1 odd with 0 will get as 1, which is same as that of original. So whenever you odd any value with 0, it is going to produce the same one. So 8 odd with 0 will get as 8. 7 odd with 0 will get as 7. 6 odd with 0 will get as 0. 5 odd with 0 will get as output is 5. 4 odd with 0 will get 4. 3 odd with 0 will get as 2. 2 odd with 0 will get as 2. 1 odd with 0 will get as 1. So the result is 1, 2, 3, 4, 5, 6, 7, 8. That will be moved to the destination register or not. As S is not present, it won't update the flags in the CPSR register. So this we have to write in the 32-bit pattern. This also we have to write in 32-bit pattern. Then we have to do the OR functionality. The next instruction is BIC R0, R1, R2. So this instruction will perform R1 and with the complemented value of R2. The complemented value of R2. Assume R1 is 4-bit data, that is 1111. Next R2 is equivalent to, first we have to perform the complement of R2. So R2 it is given as 01, 01. So the complement of R2 is equivalent to 1010. This R2 value after complementing we have to AND with R1. So the R1 register content is 1111 and with the complemented value of R2 which is equivalent to 1010. Between these we have to perform the AND operation. 1 AND with 0 will get as 0. 1 AND with 1, 1. 1 AND with 0 get 0. 1 AND with 1, 1. So the result which will be moved to R0 register is equivalent to 1010. The next category is comparison instruction. The comparison instructions are used to compare or test a register with 32-bit value. They update the CPSR flags according to the result but not affect the contents of register. The various instruction under comparison are CMP, CMN, TEA, TST. The syntax of the instruction is TEQ. Instruction, condition, optional, Rn, comma, N. So here, these Rn register and N are two register. This will be compared and the result will not be stored anywhere. Only updates the flags which are present in the CPSR register. The first instruction is CMP, which is for comparison of two 32-bit values. The syntax of the instruction is CMP, Rn, comma, N. So this instruction will compare Rn contents with the N with performing subtraction. So this will perform Rn minus N, Rn register minus N. Based upon the result which is obtained, this will update the flags in the CPSR register. The CMP is effectively a subtraction instruction with the result discarded. The result affects the flags in CPSR. So it performs the subtraction between Rn and N, and the result will not be stored anywhere. Just it will update the flags in CPSR register. So for this comparison instruction, no need of adding suffix s. Even if you add CPS, CMPS, it is going to do the same operation. The next instruction is CMN, which is compare negated of two 32-bit values. The syntax of the instruction is CMN, Rn, comma, N. The CMN is effectively add instruction with the result is discarded. The results will affect the flags in CPSR. So here the Rn contents will be added with N and it will update the flags in CPSR register. The next instruction is TEQ, which is test for equality of two 32-bit values. TEQ, Rn, comma, N. This TEQ is a logical exclusive OR between the Rn register contents and N value. For each, the result is discarded, but the condition bits are updated in CPSR. So this instruction will perform the exclusive OR, that is XOR operation between Rn register contents and N value. Based upon the result which is obtained after this logical XOR operation, the flags will be affected in the CPSR register. The next instruction under comparison is TST, which is for test bit of two 32-bit values. The syntax of the instruction is TST, Rn, comma, N. This instruction will perform the logical AND bit by bit between the register contents Rn and N. Based upon the result which is obtained after this AND, this will update the flags in the CPSR register. The TST is a logical AND operation. For each, the results are discarded, but the condition bits are updated in the CPSR register. So Rn register contents will be logical ANDed with N value and the result will be stored in flags. Only flags will be updated, the result will not be stored anywhere. Now we will see few instruction. Example, CMP R0, comma, R9. Assume before executing, these are the CPSR register format. R0 is equivalent to 4. So I'll write in the bit format 1 0 1 0 4, right? 4 means 0 1 0 0. R9 is equivalent to 4, that is 1 0 1 0 0, which is R9. The compare instruction will do R0 minus Rn, that is between this. If you do the subtraction, you get 0, 0, 1 minus 1, 0, 0 minus 0, 0. Here the result is 0, so which is going to update the jet flag. So in the CPSR register, the jet flag will be highlighted indicating the jet flag is set. Before this, the jet flag is in lowercase representing the jet flag is not set, that is jet is equivalent to 0. This is same as that of doing Rn and with not of n. So whenever we are performing the subtraction, we can take AND operation with the complemented value of the second data. The next category is multiply instruction. The multiply instructions multiply the contents of a pair of registers and depending upon the instruction accumulate the results in with another register. The long multiplies accumulate onto a register pair representing a 64-bit value. The final result is placed in a destination register which is a pair of register. The various multiplication instructions we are having is MUL, multiply, MLA, multiply and accumulate, SMUL, signed multiplication, long, UMULL, unsigned multiplication, long, SMLAL, which is signed multiply and accumulate, long, UMLAL, which is unsigned multiplication and accumulate, long. The difference between MUL and SMULL is the result size is either it is 32-bit or 64-bit. For the first two instruction, the result size is 32-bit, whereas for the next pair, that is 4 instruction, the result size is 64 bits. In ARM processor, we have only 32-bit registers. This 64-bit registers, 64-bit result will be placed in 2 registers. The first instruction is MUL. This instruction multiply 2 32-bit values and the result is also 32-bit size. The syntax of the instruction is MUL condition S RD RM RS. So here the register which is RM contents will be multiplied with RS register contents and the result will be stored in RD register. Here the source contents are 32-bit and the target R product is also 32-bit size. In that case we have to use MUL instruction. The MUL instruction multiply the contents of RM and RS registers and the result is stored in RD register. We can write the functionality of this instruction as RD is assigned with RM into RS. If S is added as suffix for MUL instruction, it will affect the flags in CPSR register. The next instruction is MLA, which is multiply and accumulate 2 32-bit values. The syntax of the instruction is MLA, condition is optional, S is optional, RD, RM, RS, RM. So here the contents of RM and RS, first it will do the multiplication. After this it is going to be accumulate the RM contents that will be stored into RD register. It is also a 32-bit result. The MLA instruction multiply the contents of RM and RS register and accumulated with RN register. The result stored in RD register. The functionality we can write as RD is assigned with RM into RS plus RM. If S is added as suffix for MLA instruction, that is MLAS, then this will update the flags in CPSR based upon the result which is obtained. The next instructions are long multiply instruction. The long multiplies accumulate onto a pair of registers representing a 64-bit value. The final register is placed in a destination register or a pair of register. The syntax of the instruction is instruction followed by conditional, which is optional, RDLO, RDHI. These are the 64-bit result, and the source data is RM and RS, where these two registers will have the 32 bits data. The various instructions we are having is SMULL, UMULL, SMLAL, UMLAL. The long multiply instruction produce the result is 64 bit. The result is too large to accommodate or to fit into a single 32 bit register, so that the result is placed in two registers that we are taking as RDLO and RDHI. RDLO is the lower 32 bits, whereas RDHI will take the higher 32 bits of 64 bit result. SMUL, which is signed multiply long to 32 bit value, and the result is 64. Here the contents of RM register will be multiplied with RS. Here it is a 32 bit size. RM is also 32 bit size. The result is 64 bit size. Out of these 64 bits, the lower 32 bits is placed in RDLO. The upper 32 bits will be moved to RDHI. The SMUL instruction is a signed multiplication of RM and RS register contents, and the register RDLO contains the lower 32 bits of the result, and the register RDHI contains the higher 32 bit of the 64 bit result. So the functionality of SMUL we can write as, after multiplying two 32 bit values which are in RM and RS register, which will produce a 64 bit result. Out of this 64, the lower 32 bits are placed in RDLO, the upper 16 bits are placed, upper 32 bits are placed in RDHI. If S is added as suffix to SMULL instruction, it will update the flags in CPSR register based upon the result obtained after multiplication. The next instruction is UMULL, which is a unsigned multiply long to 32 bit values, and the result is 64 bits. The syntax of the instruction is UMULL, condition S, RDLO, RDHI, RM and RS. Here the contents of RM register, which is 32 bit size, will be multiplied with the register RS contents of 32 bit size. The result which is produced is 64 bits. The lower 32 bits are moved into RD low, whereas upper 32 bits are placed in RDHI register. The UMLL instruction is a unsigned multiplication of RM and RS registers contents, and the register RDLO contains the lower 32 bit of the result, and the register RDHI contains the higher 32 bits of the 64 bit. The functionality we can describe as RM multiply with RS, which is 32 bit by 32 bit multiplication. The result is a 64 bit, out of which the lower 32 bits are placed in RDLO, the upper 32 bits are placed in RDHI. If S is added as suffix to this instruction, then it will update the flags in the CPSR register. The next instruction is SMLAL. This instruction is used for signed multiplication of two 32 bit values, and it will accumulate. The result size is 64 bits. The syntax of the instruction is SMLAL, condition S. This condition and S are optional. RDLO, RDHI, RM and RS. So this instruction, first it will multiply the two 32-bit values which are exist in RM and RS. Whatever the product which is a 64-bit size, that will be added to the previous register contents of RIHI, RD low. Multiply followed by accumulation. The SMLAL instruction is a signed multiplication of RM and RS registers and accumulate the product to the register pair RDHI and RDLO contents, and the result again it is a 64. Out of 64, the lower 32 bits are moved into RDLO and the upper 32 bits are moved into RDHI register. The functionality of SMLAL instruction we can write as RM multiply with RS. These are going to be accumulated with the previous values in the registers RDHI, RDLO. If S is added to the suffix for this SMLAL instruction, it will update the flags in the CPSR register based upon the results obtained after multiply and accumulate. The next instruction is UMLAL, which is unsigned multiply and accumulate long of 32-bit values, and the result is 64-bit size. The syntax of the instruction is UMLAL condition S RDLO, RDHI, RM, RS. So here the contents of RM, which is 32-bit size, are multiplied with the RS register contents, which is 32-bit size. The result which is produced, that is product, which is a 64-bit, will be added to the previous results which are existing in RDHI, RD low, and the obtained after accumulating the 64-bit results, again it will be moved into RDHI, RD low register pair. The UMLAL instruction is a unsigned multiplication of RM and RS registers and accumulate the product to the previous results which are existing in RDHI, RDLO contents, and the result obtained after accumulator, which is a 64-bit. Out of 64-bit, the lower 32 bits are placed into RDLO and upper or higher 32 bits are closed in RDHI. The functionality we can describe as RDHI, RDLO is assigned with RDHI, RDLO added with the product of RM into RS. If S is added as suffix, the result will update the flags in the CPSR results. So this about the various instruction under data processing instructions in ARM processor. Thank you all. So today we have discussed move instructions, arithmetic instruction, logical instructions, comparison instruction, multiply instruction, which are supported by ARM processor. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.